but it's pretty busy.
Okay, let's go. So I'm Jacob. I introduced myself earlier this evening, so I'll skip that part and dive right into it. So today I'm going to talk about ZoKrates. Some of you might have heard of the tool, some may not, and I'm just going to give you a high-level introduction and then dive deeper in some aspects that I think may be relevant for you. So what's the basic idea? What is this even about? So in blockchain networks, what we traditionally have is that there is a transaction, it gets sent to the network, and it is then processed on every single node in the network redundantly. And I think Truebit came to change that, and we came to change that as well, just with a little bit of a different idea in mind. So the idea here is that we process transactions off-chain, so you maybe send it to the network, and then it gets sent to some outside party, some third-party node that's not part of the blockchain network, and that executes some logic and only writes the result back to the blockchain. The result is then verified. The correctness of the off-chain execution is verified in that step, and then you can be sure that the transaction was executed correctly, and you're close, depending on the security assumptions you make in that step, to the guarantees that you have in the on-chain processing case. So what's the benefits? One is scalability. If you don't have to re-execute every transaction in the network, you can increase throughput. And also you can, like, the block complexity limit that you usually have does not necessarily apply because you only have to do the verification step on the blockchain, and you can have more complex transaction processing logic of the blockchain. Also, you can gain confidentiality or privacy, however you want to call it, because you can use private information in that off-chain processing, and if you use the right mechanism, not reveal it together with your correctness proof and the output of the operations you performed off-chain. So that's the second plus. What are approaches for doing these things? Truebit is one. I think everyone knows Truebit in more detail. And this is a more economic approach than we take it here. There is approaches using trusted hardware, so it basically shifts the trust boundary, and then you get a certification from whatever Intel SGX processors, for example, and you check attestations on chain, and depending on whether you're happy with trusted hardware or not, you can accept that as good or not good off-chain processing. And then there's non-interactive knowledge proofs as another technique you can use, and here you get a mathematical proof. Depending on the mechanisms you use, there's different cryptographic assumptions behind it, and then you can check the proof on the blockchain and have the proof being generated off the blockchain. And this last aspect, the non-interactive zero-knowledge proofs, that's the approach ZoKrates is all about, and that's the approach I want to focus on and tell you a little bit more about. So first, zkSNARKS, because that's the underlying mechanism we use, so I have to introduce it very briefly. zkSNARKS is a special type of zero-knowledge proof, and it stands for zero-knowledge, succinct, non-interactive argument of knowledge. A key property is that these proofs are very short. They're only a couple of elliptic curve points, and they're very compact in size. Also, they're non-interactive. That means it's not like in traditional PSP interactions where there's multiple interactions between a prover and a verifier that are required to convince the prover of the fact, but it's only one proof that is sent to the verifier and that can then be checked immediately without further interaction. Of course, that fits very well with the blockchain transaction processing model where one node sends a transaction to the network. These things are zero knowledge. That means you reveal nothing but the fact. If you do a complex processing that uses some private input data and generates an output, the private input that was used to generate the output does not become public. The information can be kept private without negatively impacting the security of the proof. So you learn that a computation was done correctly, but you do not learn which private information has been used to arrive at the output. You only learn it's correct. Okay, and the proof, the abstraction the proofs work on is that you know is you can show that you know a satisfying variable assignment for either an arithmetic circuit or for rank 1 constraint system. Now, what does that mean? Arithmetic circuits, you can see on the left side, they look like binary circuits where you usually have AND and OR gates or whatever, only that here you can only have addition and multiplication gates. So the challenge now is, if you want to prove some computation, you first need to transform it into an arithmetic circuit, and then you can apply the mechanisms that the zkSNARK provides you. Another abstraction that's pretty similar, not quite like it, but can also be used to formulate zkSNARKs on are ranked 1 constraint systems, and they're big linear constraint systems in the end, where each constraint can have 1 multiplication and several additions. That's the abstraction to have. So that's not quite convenient for developers to write programs in, and that's essentially a challenge we try to address. Some more background that we need to talk about one of the weaknesses that come with zkSNARKs, because up to now it all sounds too good to be true. Basically, there is a setup phase required that has to be performed once for a given program or off-chain computation, as you may say here, before you can generate proofs, and that is referred to as the setup phase. And in that setup phase, you need to trust the person who performs the setup phase to behave honestly, and only if the person behaved honestly, you can later on trust the proofs. If that person was cheating, you could not trust the proofs that were later on used. They could be faked. Now, that's not a focus of our project, but there is approaches to employ multi-party computations to mitigate these problems. In the Zcash network, for example, they had a multi-party computation in their first initial network launch to make sure that this setup was performed correctly and the trust distributed over all participants in the setup. And now for their next release, they did a much bigger global setup phase where everyone who wanted could get involved, so the trust requirements are even lowered. So there's ways to handle that. After you did the setup phase, you can execute your program and then generate proofs that shows that you executed it correctly, and then you can verify the proofs. And for the proof generation, you need a prover key, and can supply certain inputs, and for the verification of the proof you need a verification key and then the proof that was generated beforehand. Here I showed in just another way. There is that one-time setup phase always when you want to prove something regarding off-chain computations, and then after you did that setup phase you can reuse the outcome of the setup, and that's the proving key and the verification key, to do the similar things over and over again. That means for one given program you do the setup once, and then you can execute it multiple times and provide proofs certifying correct program execution as many times as you want, essentially. Okay, so that's for the background. A little example, here we have an arithmetic circuit on the left side. It multiplies x and y and arrives at z. So first, if you want to prove the correctness of that computation, you do the setup phase once, and then you can use the proving key as input for the prover, and then you find, that's another challenge that's not covered in here, how you find that, x, y, and z that fulfill this equality condition. And then after you found these values, you can publish z plus the proof that you actually satisfy this constraint system, but the verifier only learns z and the proof that and can verify the proof that you correctly found x and y, but you never reveal x and y. So that's that in a nutshell. That's what's out there. That's like the mathematical tooling that's available and published. And here's where ZoKrates comes in. As you see in these arithmetic circuits and the rank 1 constraint system, they're not quite convenient abstractions for people to write programs in. So there is libraries that allow you to write low-level constraint systems, and it can be done, but you need to dig really deep, understand a lot about the details, then hand optimize that stuff, and it's quite hard to do. So the vision for ZoKrates is to provide a more usable abstraction and tooling to bring zkSNARKS to developers. So we want to support the complete process from specifying a program to generating proofs and verifying them on the blockchain. And here we target Ethereum as the platform of our choice, although it could potentially be used with other platforms as well, because only the verifier, which is a very small component, is blockchain specific and needs to be executed on-chain. All the other stuff is covered by the toolkit and happens completely off the blockchain. We want also, and that's kind of work in progress and happens in conversation with other projects, act as an integration platform, because where we're at now is that these circuits or rank 1 constraint systems, they're not quite portable. Every library that uses these tools has their own abstractions, their own data format, and it's very hard to provide any portability between those tools, and that's quite inefficient, and that's what we're also trying to bridge that gap that we see there. That's another goal. So what do we have? What does the ZoKrates software look like? It provides a high-level language in which you specify your programs that you want to be executed off the blockchain, and then a compiler which takes this input in that high-level language and compiles it to a provable constraint system. In other words, in one of the abstractions I showed you earlier that you can then do proofs on. We provide tools for the setup phase, the witness computation, which means finding a satisfying variable assignment for these systems, and in other words, that just means executing the off-chain program. In the example we had earlier, that's finding x and y that equals, multiplied together equals the c of your choice. Okay, then we have proof generation, and we can also generate smart contracts that can then deploy to Ethereum to verify the off-chain computation. So you have seamless integration there. We're also working on the circuit import from other tools. That's work in progress. There are no standards yet. We hope that there will be standards soon, so we can leverage existing circuits that are out there more efficiently. This is the part where we currently spend most time on that we want to develop. So that's the higher-level programming language. Until now, we only have one primitive type, and that's prime field elements. You can think of it as huge prime numbers, as huge positive numbers that are smaller than a huge prime number. But that's also, you can do a lot of things with it, but it's not a very convenient abstraction because people are used to other data types that do overflow in a predictable way. So we're currently looking at including more data types that internally translate into prime fields elements, so we can map it into the constraint system, but that provide an even better, more usable interface to actually write applications in. Also, we just added SHA-256 hash functions, which are very important for commitment schemes and secret sharing schemes that you would want to implement with zkSNARKS. Then you have the things you know from other programming languages: loops, imperative statements, assertions, conditionals, and functions, and also imports of other source code files. So you write your programs as you're used to, and we're extending it so it becomes even more convenient and powerful. Together with that, we always have to make sure that these abstractions we build can efficiently be compiled into a set of constraint systems. So this is one of the main challenges. The code we generate needs to stay efficient. If the number of constraints blows up, it may still be correct, but then we lose practicality, and we want this to be usable. So we always have to, together with evolving the language, come up with good optimization techniques. From an end user perspective, what's the process when you want to use the tool? First of all, you write your code in the high-level language I just showed you, and then you compile it into flattened code. Flattened code is essentially just a set of conditions, but it has some additional information of how you can calculate intermediate values that are required later on. you can then do a setup phase based on that flattened code, which represents your off-chain computation, and that gives you a verification key and a proving key, which you can reuse for all computations that use the same high-level code. So if you have one program and different inputs, and you want to generate proofs for different inputs, you only need to do the setup phase once, and all you then need to do is reuse the proving key and the verification key. Based on the flattened code, you can also execute the program, and here it's called to compute a witness because it means finding and satisfying variable assignment, and together with a witness and a proving key, you can then generate a proof which attests that you computed your high-level program correctly and that the output actually equals what you published with the proof. You can then generate a smart contract, an Ethereum smart contract in that example, that uses the verification key to then verify proofs on the blockchain, and then you take the proof and the output, send it to the verification smart contract. The contract checks whether the computation was executed correctly or not, and then you see a result on the blockchain. Okay, so here's one important thing I want to show you. As the complexity of your program increases, the program you compute off the blockchain, the proving time and the witness computation time also increase with the complexity here. That's why we need to do the optimizations to keep the slope of these curves pretty small. But the important property, why this is cool and why this can also be leveraged for scalability in blockchains, is that the verification time is constant and not depending on the complexity of the off-chain computation. So in theory, if you have a very, very good compute node and a lot of memory, you can do very, very complex off-chain computations and still verify on the blockchain and with constant cost. Okay? Another cool thing that's not included yet, but that we would like to include, these operations, the proof generation, for example, it's highly parallelizable. So if you had a strong cluster and did all the steps in parallel, then you could scale this pretty well. So we think that if we included at some point a distributed proof generation, we could scale pretty well off-chain compute loads. Okay, so for the on-chain verification, in ZoKrates, we generate a proof in the end. It consists of elliptic curve points, 8 elliptic curve points. In the formalism we're currently using, there's more efficient ones. And then we can bring down the verification cost down to about a third. It's just not implemented yet. And what you provide is the parameters of the main function that you had in your initial program. That's the public inputs to your off-chain computation, and the return statement value. That's the output of your witness generation. That together with the proof you publish to the verification contract. This verification contract internally has a verification key that came out of the setup phase and has 7 elliptic curve points, and then performs a verify operation, and then it uses the new, or they're not quite new anymore, but the precompiles that were added with the Byzantium release to do pairing checks and other elliptic curve operations to validate the proofs. It costs currently, with the current formalism, 1.6 million gas, and as the number of public inputs or return statement values increases, it becomes linearly more expensive, but it scales quite well. I think up to 80 or more inputs until you would reach the block limit. And there's always options to optimize that by summarizing multiple field elements in one other field element. So there's some tricks you can do for optimization here.
One question there.
Yeah.
So, did I understand that the cost basically depends on the complexity of your circuit? The bigger the circuit, the more expensive.
That's what I tried to show on this slide.
Yep.
The verification
time is constant, and does that just mean it's like constant for any circuit that I use?
Yes. That's the key insight from this slide basically. When you have a more complex circuit, the proof generation time goes up and the witness computation time goes up, but they're both off-chain. And the on-chain part, which is the verification, it stays constant in cost. So that's why we can also put a fixed gas cost or a fixed gas value on that.
So the soundness and completeness stays the same?
Yeah.
In other words, like if you have a larger circuit, you might think that the chance that your SNARK behaves correctly decreases.
Yeah, that's not the case here. Like, okay, but at some point, okay, there is a bound on the number of gates where this holds, and if you increase that bound, then it would become more expensive again. But we assume that we're below a certain number of gates in a circuit, and for that number of gates, this holds.
That's just like a finite absolute, so you can fix any number there, and that fixes the amount of your completeness parameter or whatever. No? I guess, how many gates? Do you know?
I don't quite remember. 2 to the 64. Christian, do you remember?
I think 2 to the 32.
2 to the 32. Yeah, but it's really large.
How do they choose that number?
Yeah, you can also increase the number, but then all of these steps become more expensive that you do beforehand. For the new zcash setup phase, for example, they only did it in a way that the zcash circuit fits, but they also potentially, if you have very complex circuits, plan on doing another setup phase with a higher bound on the number of gates you would have.
By the way, so this 1.6 million gas will probably go down to something like 500,000.
Yeah.
How much?
So they did some benchmark. So in some situations the complexity went down to 1/10, but so something like 1/3 is probably realistic.
And also there is more.
I guess that's a different question.
More efficient.
Let's go to the end.
But it's still, is that a switch to WebAssembly or?
No, so Go Ethereum used a less efficient implementation of the curve operations.
I see, it's the specific, the opcode itself got cheap?
Yeah, the
So you could just change the number of gas by changing, can't you set that arbitrarily anyway?
It's a hard one. It's set arbitrarily, exactly.
Right, oh, I see, so they're choosing to decrease it by 1/3, but they could have done it by 1/5 as well, it's not, right, okay, that's.
Yeah, so there was just a random
make it free.
based on. Yeah. So there's two ways this becomes cheaper. So as mentioned, as the implementations become more efficient, the Ethereum network can put a lower gas price on the elliptic curve operations, and then cost goes down. And there's also a more efficient SNARK construction, which would also bring it down by 1/3. Roughly, I calculated it that way, and then it would be quite a big reduction in cost if you take both measures together. But that second formalism, it's Croth 16 SNARK, we did not implement it up to that point. But then the verification becomes cheaper. That happens on chain.
I have a question about that being constant. You mentioned that it scales with the input size, but if I replace my inputs with just the hash of the input and the outputs with the hash of the outputs, do I then get a constant size, a constant verification cost at the expense of more proof time?
Yeah, I would say so. You then need to check the hashes. Yeah. So that's one of the tricks I mentioned. You can also hide, if you know upper bounds for the size of field elements, you can hide them together in one new field element and then check that this deconstruction was done correctly in the circuit. There's different ways, and that would be one way how you could optimize. Okay, but then again, the result would not become public in clear text, but only the hash, so you always have to see which information you want to become public and which not. So here, because we're at a Truebit event, I want to briefly talk about how ZoKrates and Truebit relate, and I think they're in a quite cool relation, because what you could do is you could use Truebit to off-chain verify the ZoKrates zkSNARK verifier. So then that would take even more off the blockchain, and only in rare cases where there is a dispute, you would need to move on chain, and then you would only need to check one step in that verification contract. So that would be quite cool. The downside here is that you kind of lose some security guarantees, because in Truebit it's an economic model, whereas here it's a mathematical model, and then you kind of move from strong mathematical proofs, although some argue it's not that strong because it's based on some non-provable assumption in that concrete case, but you move to an economic model, but still that would scale very well, and I think that could be cool. You have a question?
No, it's that light behind you. I'm trying to read this. Let's hope not.
Great.
Okay, and also,
is this a good time to vote for the gas on bulletproofs?
Bulletproofs, now with bulletproofs, the verification cost is no longer constant, so that's why on-chain verification is a bit more difficult. But they build on the same abstraction as the zkSNARKs. So we can also use the ZoKrates front end to compile down to constraints, and then build use bulletproofs to generate another type of non-interactive proof on top of that. And if we could then write a verifier that is too expensive on the blockchain, but again use Truebit to overcome that limitation of the blockchain, then we could combine both and even verify bulletproofs that would not be verifiable on the blockchain in the first place. And for those of you who don't know bulletproofs, maybe I should mention it's a similar non-interactive proof construction, but it does not require a setup phase, a trusted setup, so that limitation is removed.
I just want to parse this. First of all, why would you want to do this? If you already have something that can verify in constant time, why would you want to make it
because it's cheaper, right? If I don't have to verify on the blockchain.
For the prover, you mean?
If I do, also from a network perspective, if I do not have to verify every proof on the blockchain in the first place, because I use Truebit and there is no challenges happening, then I do not put any load on the blockchain.
So what do you mean by less efficient here? I mean, you're making, it's not, assuming
okay, here in the second
Jason,
sentence.
let's end the presentation, then we'll do a Q&A. I think let's.
Okay, the good thing is, that's my last slide. Okay, so as I said, we doubled our team size this year, and I would not mind doubling the team size again. So if you feel like this is interesting to you, you can contribute in one of the areas, being it language design or the crypto stuff on the lower level. We're happy to see contributions or just engage in conversations. Here's the GitHub link. You can always reach me via email as well. And credits go to Christian for always brainstorming about the project and implementing the Ethereum precompiles that made verification possible in the first place, and Thibaut, who also joined the team recently. Yeah, that's it. Now let's take some questions. I go back one slide. Okay, so what I meant here, in the bulletproof case, the verifier is no longer constant in cost, and that's why you cannot generally verify these proofs on the blockchain.
Ah, you mean the bullet?
Yeah.
You're no longer doing a snark.
Yeah, exactly.
Oh, then it makes sense. So then that answers my second question too, because the zero knowledge, you could have built it into the bulletproof, and so
Awesome.
that needs to be emphasized here is that the bulletproofs don't have a setup phase that produces toxic waste.
Exactly. Yeah.
Which is a big downside of the zkSNARKs, because you need to trust someone that they actually deleted a piece of information that will compromise the whole
That's
system.
the reason you do it, I guess.
Yes.
Yeah, so we also prototyped an on-chain version of the multi-party computation setup the Zcash people did. It's kind of still work in progress, but there could be a way that you do the setup phase via the blockchain in a way that you have 1,000 participants and you reduce your trust assumption to 1 out of n for external parties, and if you participate in the setup and behaved honestly, then you have the guarantee that the setup was done correctly. But still, something like bulletproofs or another mechanism that does not require a trusted setup would be cool.
Is bulletproofs the kind of modern version of SNARKs?
It's a different version of SNARKs. The proof size for SNARKs is huge. That's why I think verification in a non-custom blockchain built for that is probably very difficult.
It's kind of in between, isn't it? So bulletproof still requires a randomness beacon,
Yeah.
and SNARKs has no requirements at all. Do bulletproofs require cryptographic assumptions or not?
I'm not sure, to be honest.
So I think they do. They have right. They rely on discrete logarithm and SNARKs.
Okay, but that's better than zkSNARKs because
SNARKs have no assumptions.
yeah, so I assume that.
discrete logarithm.
Yeah.
Well, what are the assumptions you were talking about for SNARKs? These kind of questionable assumptions, or for SNARKs?
Yeah, there's that knowledge of exponent assumption which cannot or has not been proven correct. Also, there has been no counterexample, so it's an assumption that was made that is kind of accepted in academia, but it's an unproven assumption.
So, quick question. You mentioned that you have a language, right?
Yeah.
So you implement the cryptography algorithms inside this language, or just using other libraries?
For now, we only have SHA-256 as a hash function, but there's no implementation yet of more complex crypto algorithms.
But what I mean, just do you implement the SHA algorithm using your language?
We have two approaches. We have one implementation in our language, it works, and we're currently, for efficiency, because it can be faster, also that's the interoperability part I was mentioning, trying to import a hand-optimized circuit that is even more efficient. But we have an implementation in that language and it works.
Yeah, because at some point I trust some sort of algorithms that is written in a certain way.
Yeah, that's a very basic problem. You kind of always trust our compiler to correctly generate circuits. It's open source, you can check it out. But yeah, it's like with regular programming languages, you trust the compiler to translate it in a way that it is what you expect.
What sort of sample applications have been used to do this besides the simple multiplication example you gave?
Okay, so we did a commitment scheme using hash functions. We did Sudoku verification just as kind of a fun thing, and we're implementing, but it's not that far yet. ERC20 token that's privacy preserving. Yeah.
Could you give indications of what the proof generation time is on a modest computer?
Yeah, I did some benchmarks for a research paper, but it's very hard to say because it depends on the number of constraints, but not only that, but also on the density of the constraint systems. So for the SHA implementation in that language, it's currently below 1 second, if that helps, but we need to...
But it's really application specific, how long the...
It's totally application specific, depending on circuit size, and it also depends on how well we do our optimizations. Like if we do no optimizations, then prediction becomes easier because the rank 1 constraint system we have is very sparse, but if we do good optimizations and put a lot in the constraints, then the number of constraints no longer is something that can be used for good predictions regarding the proving time. Okay, yeah?
What sort of things are the hardest to compile down to efficient constraint systems.
What really sucks is comparisons on field elements, like less than, equal, for example, because for that, to do that, or at least we found no other way yet, you need to do a bit decomposition of the field element, then compare and make sure that the bit decomposition is actually correct decomposition of the original field element. So that's quite inefficient, and I would love to find a more efficient way to do that, but I haven't found one yet. Okay, thank you.